This section is going to go back and talk about analyzing a graph. We had done this previously with just the first derivative, but now we're going to throw the second derivative into the mix. The front of these notes give a nice review of all the things about graph analysis that you need to know, starting with that connection between f prime, and now f double prime. Over here, I have it listed out the connection between those three graphs. I'm going to draw your attention to the fun chart over here. In this fun chart, it gives that connection just in a visual sort of way. So if you struggle to keep things straight, maybe this will help. This FUN here, that's why it's called the fun chart. And the U and the N are actually a concave up shape and a concave down shape. And the symbol here means increasing, and this means decreasing, and of course a plus means positive and a minus means negative. How this information is lined up in rows and also in columns is important. So when you write this, you'll want to line it up exactly like this. And what this is telling us is that when F is concave up, F prime is increasing, and F double prime is positive. When F is concave down, F prime is decreasing, and F double prime is negative. When F is increasing, F prime is positive, and when F is decreasing, F prime is negative. So it's just all those relationships shown in a visual format. We could also extend this a little bit by looking at the in-between, the increase to decrease, and that is where a max would occur. When F goes from increase to decrease, and you can see a maximum would occur if I were to connect these two pieces, increase to decrease, at that moment, that is where F prime is going positive to negative. And the point of inflection is going to show up on this in-between. These two columns right here is where you'd find information about a point of inflection. A point of inflection on the graph of F is where we change concavity from concave up to down. On the F prime graph, this is what a point of inflection on F looks like. F prime would be going increase to decrease, and F double prime would be going from a positive to negative. It only addresses one way for that point of inflection. You could interchange the two columns, and that would be a point of inflection going that way as well. So concave down to concave up on F is a point of inflection. If I go from a decrease to an increase on F prime, or negative to a positive on the graph of F, all of those indicate a point of inflection on the graph of F. If you like this idea of the fun chart, then use it. If you don't, and you can just remember these relationships just by memorizing them, then that is fine as well. I want to quickly go through the other information on this sheet, just so you know what's here. Whenever you're asked to justify an answer, you want to always name the graph. You want to name it as it's named in the problem, F prime, F double prime. Never call it the graph. Never call it it. You have to be clear and communicate which graph it is you're talking about. Critical points, critical numbers, critical values, critical anything is talking about this. It's where F prime equals 0 or F prime is undefined. And when you find those values, they can either turn into maximums, minimums, or neither one, depending on how the sign changes around them. Next up is absolute max and min. We talked about this in section 4.2. The telltale sign that you're being asked to find a max or min is a closed interval. If you have an open interval, there's no way you can find an absolute max or min. Whenever you're asked to do that, you want to use a global argument, and what that means is you're going to consider critical points and endpoints. You're going to do this candidates test, and you're going to do that table. You're going to list the critical points and endpoints in that table and find their F values to draw your conclusion about absolute max and absolute min. Points of inflection are just where F changes concavity from concave up to concave down or vice versa. This was actually covered in the fun chart, but it's important to know. F prime equals 0 and undergoes a sign change. So make sure when you find points of inflection that you verify that second derivative goes from positive to negative or vice versa. If you're looking at the F prime graph, you want to be looking where F prime goes from an increase to decrease, or vice versa. And again, this is covered up in this sign chart up here. We had identified the point of inflection is happening in between these two columns, and you see that f double prime going positive to negative and f prime going increase to decrease. Next is our first derivative test for extrema, and this looked at the first derivative to tell if you had a max or a min, and you just paid attention to that sign change. If f prime goes positive to negative, we have a max, and if f prime goes negative to positive, we have a local min. We can also use the second derivative to identify extrema. When f prime of c equals 0, that indicates that you have a possible max or a min. This part right here, to say f double prime is less than 0, means that you have a concave down portion. And if you have concave down, then that place where that tangent line slope is 0 has to be a max. And just turning that around, if f double prime is greater than 0, that means that I have a concave up shape. So the place where my tangent line is 0 is going to be at a minimum. So this identifies a local minimum. In general, the first derivative is going to give away information about max, min points, increasing and decreasing intervals. And the second derivative will reveal information about points of inflection and concavity. This word horizontal tangent shows up a lot. All that means it's where the slope is 0. So f prime is our slope of f. We want that to equal 0. The last 2 points are just helping you out with when to use brackets and when to use parentheses. If you have a closed interval that you're finding the maxes and mins, you'll want to use brackets, these squared off brackets, so that you're including the endpoint in your interval. Whenever you have an interval that has an infinity or negative infinity, you'll want to pair that with a parenthesis. Let's look at a few examples. Some of this will be review and some of it will be new. We're given a function f. We're told f is differentiable on this closed interval from -6 to 5. We're given a value of f of 3 equals 6. This is a graph of f prime. So we're looking at f's derivative. What we have is a semicircle, and then these are just straight line segments. I've pulled our fun chart in here to help us know what to look for. On question number 1, it says, on what intervals is f increasing? I look, here's f. I see a little increasing picture here. So what I'm looking for in my f prime is a positive. This is f prime, and positive means above the x-axis. So this graph is above the x-axis on these intervals, and I list those as my answer. So from -6 to -2, I put a bracket on the -6 and a parenthesis on the -2. And then from 2 to 5, I did not put a bracket on the 5 because 5 is actually sitting on the x-axis. So I went ahead and put a parenthesis on that because f prime is positive. The next question asks where f is decreasing. F is decreasing. So here's f decreasing. I'm looking for an f prime to be negative, and that means below the x-axis. So it's this half circle interval right here, and it looks like we're going from a -2 to a 2. I list my interval because f prime is less than 0. So if you don't like to say f prime is negative, you could say f prime is less than 0. It's just another way of saying the same thing. Question 3 is asking where is f concave up? This is a new type of question for us. If I look in my fun chart, I can see f is concave up is this picture right here. What I'm looking for in an f prime graph, because this is an f prime graph, is f prime is doing this, increasing, literally increasing. So as I trace along f prime, I see that f prime is decreasing, 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 decreasing. Once I move to the right of the y-axis, now this is an increase in f prime. I hit a little snag right here, but it continues to increase all the way until I get to that x value of 3. My increase interval goes all the way from an x value of 0 to an x value of 3. This blue piece is my interval of increase. And my reason is just what I was looking for in that graph. F prime is increasing. Next, I'm asked to find where f is concave down. In my fun chart, here's concave down. And what I'm looking for in my f prime is a decrease. My f prime graph is decreasing all the way until I get to the y-axis. Then it shifts to an increase, increase, increase until I get to that tippy top at x equals 3. Once I move past 3, back on the decrease. there are two intervals of decrease. I just list these green intervals, -6 to 0, 3 to 5. My reason is just what I was looking for in this f prime graph, which was a decrease. F is concave down when f prime is decreasing, and that is my reason. Question number 5 wants me to look at the graph of f prime and say where f has relative minimums. In our fun chart, we identified this in-between column is where a max would be occurring. When the opposite happens, that's where a min would occur. F would go decrease to increase, and my f prime would go negative to positive. In my graph, as I trace along, this is positive, and I switch to negative right here. So I go from positive to negative at the -2, and I go from negative to positive at the 2. The minimum is this one right here, where I go negative to positive. That's my min, and this one over here is going to be my max. This takes care of question 6 as well, which asked for a relative maximum. When my f prime goes positive to negative was my maximum. When my f prime goes negative to positive, that's my minimum. Make sure you pay attention to the justifications on this. F prime goes negative to positive for the min. F prime goes positive to negative for the max. Question number 7 is asking us to identify where f has a point of inflection. On our fun chart, our point of inflection was this in between. F has a point of inflection, concave up to concave down, where f prime goes increase to decrease or the other way around. When I look at my f prime graph, I'm decreasing, decreasing, decreasing. I'm decreasing all in here. I switch to an increase at this point right here. I go increase, 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 and I switch back to a decrease at the 3. At x equals 0, I switch from decrease to increase, and at x equals 3, I switch from increase to decrease, so those are my 2 points of inflection. My justification is exactly what I was looking for in this f prime graph. F prime goes increasing to decreasing and vice versa. You don't have to specify which one, increase to decrease or decrease to increase, goes with each of these points of inflection. You can just collectively write your reasoning like that. The next question, number 8, wants the equation of the tangent line. It's the question that never really quite goes away. To write the equation of a tangent line, you need a point and you need a slope. If I'm tangent to f, I need f of 3 and f prime of 3. I'm looking at an f prime graph. F prime of 3 is just the function value at 3, which is a 2. My f prime of 3 is a 2. To find f of 3, if you go back to the very beginning of the problem, where it had the information, it says that f of 3 is 6, and that's what I'm going to use as my point. My point is 3, 6, my slope is 2, and with that I write my equation. Question number 9 is asking which is greater, f of -6 or f of -2. When I look at this graph of f prime, here is f prime of -6 and f prime of -2. Don't make the mistake of thinking that it's asking about f prime's comparison of values. It wants the comparison of values of f. A common mistake students make is to see this point of f prime at 6 is higher, and therefore they think that f of 6 will also be greater. However, use this f prime graph to think about what's happening on the graph of f. We said that f begins with an increase. If you imagine what f looks like, f is going to begin someplace, I don't know the y value, but it's going to begin at x equals -6, and it's going to jump into an increase, and it's going to increase until I get to x equals -2. So if I start at this level and I increase to get to the other point, then it looks like the f of -6 is lower and the f of -2 is higher. Therefore, my greater value is f of -2. And I know that's true just because of my analysis. If f prime is greater than 0 on that interval, that means f is increasing, meaning f of 6 will be lower and f of -2 will be higher. That's the same thought process in number 10. It's asking us to compare f of -2 and f of 2. A common mistake is to look at this graph of f prime, and you see f of negative 2 and f of 2 at the same level, and you want to think that they neither one is greater, that they're the same. However, if you think about what f is doing along that interval from negative 2 to 2, along this interval, because f prime is negative, f is actually decreasing throughout that entire interval. If I start at f of negative 2 and I decrease to get to f of 2, then the greater value is here at the negative 2. My reason for choosing f of negative 2 is because f prime was less than 0 on that interval from negative 2 to 2. Therefore, I know f is decreasing as I move from x equals negative 2 to x equals 2. Our last two questions are about horizontal tangents. Question 11 wants to know where f has a horizontal tangent. I know a horizontal tangent of f is where its derivative equals 0. Since I'm given the graph of f prime, I can see that f prime equals 0 in 3 places, negative 2, 2, and 5. The next question is very similar, except this one is asking where f prime has a horizontal tangent. F prime has a horizontal tangent when its derivative, which is f double prime, equals 0. When I look at my graph, I can see that its derivative equals 0 right here where I bottom out, here at x equals 0. So that's where f has a horizontal tangent. And saying this part where f double prime equals 0, that is my justification. I'm just saying what is it about this graph that made me pick x equals 0.